Welcome to our fourth video on NMR spectroscopy. In this video, we'll be looking at more NMR spectra, along with our third major piece of spectral information that we can interpret to determine the structure of a compound. So to get started, we'll work another practice problem. So what I'd like for you to do, and we've done this a few times already in this video series, is to sketch the proton or 1H NMR spectrum of this molecule. So we're doing NMR for hydrogen atoms. And just a reminder that the carbon-carbon bond in this compound rotates faster than the NMR timescale. So you'll need to take that into account when you assess equivalency. So pause your video and make a rough sketch of the proton NMR spectrum of this molecule now. Okay, so hopefully you've been able to make a sketch. Don't worry too much about whether your chemical shifts are super accurate or not. Really what I would be worried about at this point is relative chemical shifts, so like which signal or signals are downfield of others, for instance. So here's the NMR spectrum of the compound, and this looks pretty different from what I think you probably were expecting. You can see that there are kind of like two signals, certainly in the way that they've been integrated, but there appear to be multiple lines in each of these signals. And then you'll also see a signal at 0 ppm way on the right-hand side of your screen that's labeled TMS. So that's our chemical shift standard. Remember way back in the chemical shift video, we talked about these shifts as being relative to a reference. And that is the reference compound tetramethylsilane, or TMS. So that's really not from the compound that has the 3 chlorine atoms. It's distinct. We're going to focus on the two signals that are labeled with color. So you can see that there are a total of 5 lines across these two lumps. And if that's true, how many resonance frequencies is the NMR actually picking up? Yeah, it seems like there should be 5. Each line is its own chemical shift value, its own position on the x-axis, and that's going to correspond to a specific resonance frequency. So there seem to be 5 different kinds of photons coming from this compound, even though there's only 2 kinds of hydrogens, which is a little bit concerning and certainly not something we've talked about before. So let's interpret this in a more critical way. So we know that if there's 5 resonance frequencies, that there must also be 5 different effective magnetic fields, or BEFs. So it looks like, based on our x-axis here, we have essentially some small variations in effective magnetic fields that are clustered around these areas. So like, for instance, we've got 2 different BEFs that are almost the same, and those give the 2 lines at around 4.0 ppm. And we've got 3 different BEFs that are almost the same for the cluster of lines just under 6 ppm. So we have this like clustering effect. To explain this, we actually need to incorporate another piece of information into our physical understanding of NMR. And that's that these nuclides, so like the proton, for instance, in a hydrogen nucleus, those also have spin numbers that are not 0, and they're charged. So when this compound is moving inside of a magnetic field, Lenz's law tells us that the nuclei generate their own induced magnetic field. It's very small. So another way of saying that is that neighboring nuclei also matter, right? So if you're nearby a hydrogen atom, that neighbor to you, essentially, will create its own induced field that you will feel. So the field that can be created can go in 2 different directions. We've talked about this before. We can either align the induced field from the nucleus with the external magnetic field, which we're labeling with that green arrow, or we can align it against, or anti-parallel. So basically what we're saying now is that our magnetic field that a hydrogen atom experiences, or BEF, is impacted by induced magnetic fields from neighboring atoms, right? So that means we need to include another term in our equation that gives us BEF, right? So now we have BEF is equal to the external magnetic field, B naught in green, minus the induced magnetic field from the electrons near a hydrogen, and then either plus or minus the induced magnetic field from the neighbors. So we'll call that last term B sub n. Well, why plus and or minus? Because your neighbor could either be in the alpha or beta state. And so if you think about how NMR works, you're looking at signals from billions of molecules, and maybe about 500 million of those molecules, a given neighbor will be in the alpha state. But in the other 500 million molecules, that same neighbor will be in the beta state. So we have like a statistical distribution here. Sometimes we add B sub n and sometimes we subtract it. And that's what gives rise to these clustering of signals. We know that chemical shift is directly proportional to Beth. So if we've introduced this third term, plus or minus B sub n, or another way of saying that is taking into account whether your neighbor is in the alpha or beta spin state, we have this clustering effect where either we could be adjusting chemical shift slightly downfield, that's if our neighbor was alpha, right? We're adding B sub n, so Beth is getting bigger. Or if our neighbor is in the beta state, in which case we would subtract B sub n, in which case Beth is going to get a little bit smaller and the chemical shift will go a little bit upfield. So these changes are not very large. You can see this equation Beth equal to 3 different terms, and those terms are listed in decreasing order of essentially intensity, or how large, literally how large the numbers are for the magnetic field. So the external magnetic field is massive relative to everything else. The induced magnetic field from electrons can make a difference. That's going to move us around pretty substantially on our x-axis because of differences in electron density, as you've seen pretty substantially already in this unit. And then our effective neighbors is quite small relative to these other 2 terms, and so we're just making small adjustments based on B sub n and whether we're adding or subtracting, which is why we were seeing that clustering effect in the spectra we saw to start this video. We have essentially the localization of the cluster of lines is being dictated by B sub I, the electron density, and then the so-called splitting of that signal, so basically getting these like fine lines that are all clustered together, that comes from B sub n. So I use this term splitting, and that's to denote this process of incorporating B sub n or being impacted by neighbors. And it goes by a bunch of different names that you'll see used interchangeably in different textbooks or practice problem sets, and even by me. And I do it intentionally. I want you to hear all these terms because depending on what you do next in NMR, if it's just the MCAT or if you're doing organic chemistry or whatever it is, different people will call this exact same phenomenon different things. So 4 terms you should be familiar with: coupling, spin coupling, multiplicity, and splitting. They all mean the exact same thing. This concept of taking a signal that's localized on the basis of electron density and then hacking it up into fine collections of lines, which are arising from the influence of neighboring atoms. Okay, so let's actually see if we can predict this so-called splitting or coupling. For simple molecules, we can typically do this just by counting the number of neighbors. And we can write a rule, which is often called the n+1 rule, where the number of lines in a signal, so think about the spectrum we saw before, we have that cluster of lines, maybe there's 2 lines for instance, is going to be equal to the number of neighbors plus 1. So let's look at an example. We'll go back to the molecule that we looked at the beginning of the video, and let's assess the signal that's coming from HA, which is in red, or excuse me, in blue. So HA has 2 neighbors, each HB atom. So HA will give a signal with 2 plus 1 lines. Or if we do the sum, we would expect the signal that comes from HA to give 3 lines. So this might be a little counterintuitive. I want to spell it out explicitly. A single hydrogen atom, like HA, can give a signal that's comprised of multiple lines. That's actually quite common. And that's what this concept of coupling or multiplicity or splitting is about. It's taking a single signal and splitting it up into multiple lines. So another way of thinking about this is that the neighbor splits a signal given by HA. So the electron density of HA dictates more or less where you are on the x-axis, and then how that signal is chopped up into individual lines will be dictated by the neighbors. This is a common place where students struggle, where you're analyzing essentially the characteristics of a hydrogen like HA, but you then have to think about other hydrogens to make that decision, right? So be clear about what you're analyzing when you do this. So let's check this work, make sure that we're using the n+1 rule correctly. So I'm just going to show you a portion of the NMR spectrum that you started the video with. So this is the signal that comes from HA. It's further downfield than the other signal because of the additivity of induction from the 2 chlorine atoms nearby HA. So here we can see that there are 2 neighbors, right? HA, like we said, will have a signal with 3 lines, and that's what we see. It's often the case that these lines are different heights / intensities. And there are specific patterns that go along with this that we'll talk about a little bit later in the video. Okay, so let's then continue our analysis of this compound using what we now know about coupling. So let's look at HB. How many neighbors does HB have? And to decide this, we actually need to answer a question. Does the other HB count as a neighbor? So if we were to look at like one of the two red hydrogens, does the other red hydrogen count as a neighbor or not? How are we to know? Well, if you're a scientist, you probably think about, rather than deriving this from theory, we could simply look at data. We could look at the NMR spectrum for this compound, and then we could work backwards from the number of lines that we actually observe. So let's do that. So I'm showing you now a portion of the NMR spectrum of the same compound. And we can see the signal that corresponds to the red hydrogens, which we know are equivalent. They're attached to the same carbon. And we see that there are only 2 lines in this signal. So if we work the n+1 rule backwards, or essentially if we solve it for the number of neighbors, we have 2 lines minus 1. So apparently, HB has only 1 neighbor. And from that, we can conclude that one HB atom doesn't couple to the other HB atom. Another way of saying that is that equivalent atoms do not couple to each other. Another way you could say that is that atoms attached to the same carbon in simple molecules are not neighbors at all. Okay, so let's work on this a little bit more, because there's one other question with respect to what constitutes neighbor that we want to address. We'll look at a different compound here, 1-bromopropane. So there are 3 different kinds of hydrogens in 1-bromopropane. I've color-coded them here as blue, red, and purple. And just to get started, since we're going to look at the NMR spectrum here, I'd like for you to practice your reasoning about chemical shifts. You know that there's going to be 3 signals because there are 3 types of hydrogens. I just want you to decide of those signals which will be most downfield and which will be most upfield. So pause your video and make your prediction about relative chemical shifts now. If we look at the structure, what we're looking at is electron density. That's going to be the thing that dictates chemical shift mostly, and then we would deal with multiplicity after the fact. So it looks to me like the purple hydrogens are closest to the only inductive acceptor in the entire molecule, the bromine atom. So I would expect the purple hydrogens to be the most downfield, and then I would sort the other 2 on the basis of distance or number of bonds to the bromine. So that means that the blue hydrogens will be the most upfield. They're the furthest away, or the largest number of bonds away from the bromine atom. So here's the simulated NMR spectrum for 1-bromopropane. I simulated it so that the lines were easier to see. And you can actually see the assignments listed here. So our assessment was correct. What we're seeing is the largest chemical shift of, let's say, about 3.4 ppm for purple. There is a collection of quite a few number of lines for the same signal that comes from the red hydrogens, and that's just about 1.9 ppm. And then at just about 1 ppm, we see the blue hydrogens. So one of the things that we can glean from this NMR spectrum of 1-bromopropane is essentially like what counts as a neighbor, like how close do you have to be? If we think about the purple hydrogens, we could say that both the red and the blue hydrogens are neighbors to the purple hydrogens, in which case we would have 5 total neighbors, and the signal for the purple hydrogen should have, let's see, 5 plus 1, so 6 lines. But we can see in the spectrum that that's not true. Instead, we see 3 lines. So we can conclude that apparently the purple hydrogens only have 2 neighbors. And really that's only going to be consistent with the red hydrogens being neighbors to the purple, but the blue hydrogens not being neighbors to the purple H's. Interesting. So what we can say is that for simple molecules, really only adjacent, or sometimes called vicinal hydrogens, count as neighbors. So adjacent would mean that it would take you 3 bonds to go from one hydrogen to the other. If we look at this with our purple and red hydrogens in the structure here, we would go from H to C, that's 1 bond, from C to C, that's 2 bonds, and then from C to H, that's 3 bonds. So that's typically what we're going to think about for adjacency. Anything more than that, so like 4 bonds or 5 bonds for simple molecules, you will never see coupling. Okay, so here's the other place where I bring in this disclaimer. If you end up doing NMR spectroscopy for reals, this rule will be a bit more complicated. In this class, what you see in red text on the slide is going to be just fine. That'll work for you. Okay, so we now know what a neighbor is. It has to be a non-equivalent hydrogen, so it can't be equivalent to you. and it has to be adjacent to you. Those things both have to be true to be counted as a neighbor. We also can describe the structures of these signals with respect to the number of lines and their relative intensities with names. And that's actually pretty common because it's easier to say a name than describe the number of lines in a signal. You're probably getting tired of me saying lines in a signal. So you can see the labels here. Singlet would be 1 line, doublet would be 2 lines, and you can see how the prefixes here, so like triplet and quart and those, or trip and quart and things like that, are going to give rise to information about the number of lines. So triplets would be 3 lines, quartet 4, quintet or pentet, either of those will describe a signal with 5 lines. I use pentet, other sources you may see quintet. And then you can see sextets and septets as well for 6 and 7 lines. So you'll also notice that the lines are all different intensities in a lot of these signals, and that turns out to be important information. Again, if you start using NMR spectroscopy in a laboratory setting, this will become important because it can sometimes be hard to know whether a spectrum or a signal, that has 3 lines is a triplet or some other kind of pattern. So for us, we will usually just be counting the lines. All right, so let's actually look at an example where we use this nomenclature and make assignments on the basis of multiplicities or coupling patterns. So here's 2-chloropropane. And so we can talk about this concept of spin coupling as essentially a census of neighboring hydrogens. If I look at the hydrogen labeled in red in the structure, I know a few things. It's probably going to be the most downfield signal for this molecule because it's the hydrogen that's closest to the chlorine. So I can find that signal on the NMR spectrum, and then I see, well, it's a little bit hard to see in this image, but that's a septet. So what I know right away, even if I didn't know the structure of 2-chloropropane, is that that red hydrogen must have 6 neighbors, and that's really useful structural information. Right? This is really where coupling is super helpful. It lets me to know something about not only the hydrogen's electron density, but what's nearby in the structure, right? And that gets back to being able to work out the structure of complex molecules like mitotoxin using NMR. This coupling will be critical for doing tasks like that. All right, so to close this video, we've now learned quite a bit about NMR, and coupling can be a little bit complex to implement sometimes. So I'd like to do a couple of practice problems. I'd strongly encourage you to work them in the order of questions that are listed on the slide here. So first, you'll actually decide how many signals there are in the proton NMR spectrum of a given compound. Then you'll decide the integration for each of your signals. Then, for each of your signals, you'll decide the total number of hydrogens. A total number of neighbors. And then finally, once you've done those things, you can assign multiplicity words. So things like doublet or quartet or pentet, whatever it might be. So we'll do this for each of the 2 structures. This will take you a few minutes. I'd strongly encourage you to work this with scratch paper and maybe colored pencils or pens if you have them. And make sure you actually write out all the implied hydrogens in these structures to get started. Okay, so pause your video, work through at least the structure on the left, and then once you have the structure on the left, you can start your video and we'll work through the solutions there. So this is a fairly busy analysis. I'm trying to use color to help keep us organized. So we'll work this from more or less left to right in the structure. So that means we'll start with what I'm labeling as the red hydrogens. So we see here that there are 3 H's that are all equivalent to each other in that methyl group, which means they won't count as neighbors for each other. And they're too far away from the blue hydrogens to couple. So really these red hydrogens have no neighbors, and that means they'll just be a single line in the signal, which we're going to call a singlet. That singlet will integrate to 3. If we then move on to the signal that comes from the blue H's, we see that there are 2 neighbors. So the magenta hydrogens are the neighbors of the blue H's. And that makes the signal from the blue H's a triplet with an integration of 2. So if we looked at the magenta hydrogen signal, now we've got 5 neighbors. The blue hydrogens, the 2 blue hydrogens, are neighbors to the magenta hydrogens. But the 3 green hydrogens are also neighbors to the magenta hydrogens. And that makes the magenta signal sextet with an integration of 2. So finally, we could look at the green hydrogens. So those of the green methyl group, these have 2 neighbors, just the magenta hydrogens, which makes the green hydrogen signal a triplet with an integration of 3. So one of the things that you'll notice straight away is that the multiplicity and the integration values aren't the same, or not typically. It would only be kind of a random fluke. if your integration value and your multiplicity, like number, I guess, were the same. They're describing two different things, right? Singlet is telling you how many neighbors you have. Integration is telling you how many h's are giving the signal that's being split. Okay, so let's, then you can go ahead and pause your video and look at the other of our two molecules, so the compound containing the iodine, and do the exact same set of analyses. If some of your assessments in the previous problem weren't the same as what I ended up with, I'd encourage you to think about where the discrepancy is coming from before you start working through the problem for the iodine. Once you've done all of the analysis for the alkyl iodide, restart your video and we'll work through the solutions. So we'll work this problem in a similar fashion to what we did before using color coding. And just a reminder that methyl groups, Me, are CH3s. So when you see that Me, remember that there are hydrogens present. So if we look at the signal for the red methyl, there'll be 3 H's there. Those H's have just one kind of neighbor, the 2 blue H's. So the signal for the red methyl will be a triplet integrating to 3. The signal for the blue H's will be a pentet because there are 3 red neighbors and 1 green neighbor, whereas the magenta methyl hydrogens just have one kind of neighbor, the green H. So the magenta methyl hydrogens will give a doublet signal integrating to 3. On the other hand, the green hydrogen has quite a variety of different neighbors here. So the signal for the green H will be an octet, meaning there's 8 lines, and that means there must be 7 neighbors. 3 of the magenta H's, 2 of the orange H's, and 2 of the blue H's. Finally, we could look at the signal from the orange H's. So there's just one neighbor for those, the green H. So the orange H's will give a doublet with an integration of 2. This is dibromo or 1,2-dibromoethane. So 2 carbons, 4 hydrogens. And I just want you, now that you know about multiplicity, I want you to sketch the NMR spectrum for this molecule. And once again, remember that the central carbon-carbon bond here is going to rotate faster than the NMR timescale. So pause your video and sketch your NMR spectrum. Hopefully you have the sketch ready. So I'm going to show you the NMR spectrum of 1,2-dibromoethane. It's just a single line. Interesting. Why would that be? Because there's 4 hydrogens, but I bet you decided that there was only one kind of hydrogen. And then I bet you probably drew a triplet. Very common. Don't worry, this was a trap. I meant to try to trip you up here. But to make a point, and that's that you have to be careful about assessing whether or not neighbors exist when you have equivalency that's more complicated than just being attached to the same carbon. So all 4 of these hydrogens are equivalent. And remember we said that only non-equivalent H's count as neighbors. So that means these hydrogens don't have any neighbors, at least as far as NMR is concerned. And we'll just get this one signal that's not split or coupled at all. All right, so that concludes our discussion about multiplicity or coupling or splitting, any of those things. They're all the same concept. At this point, you have all of the basics that are required to start working with NMR spectra. I would strongly encourage you to look at the problems listed in the SLO document with respect to like web spectra or other resources where you can actually look at NMR spectra and analyze that and come up with structures, or vice versa. Make predictions about NMR spectra from the structure itself. Those are both useful skills. So in the remaining videos of the series, we'll look at some kind of advanced topics in thinking about chemical shift, and then we'll also be looking at what's called heteronuclear NMR. It turns out that you can do NMR on atoms other than hydrogens.